So hello, everyone. First of all, I would like to thank the organizers for the opportunity to give a talk in this workshop and everybody for being present today. So today, I will discuss an alternative approach for constructing black hole steady states to the Einstein-Vlasov system. First of all, I will show how to make the construction in the case of spherical symmetry. Then I will talk about how can we generalize the method to the axisymmetric case. So the study of the Einstein-Vlasov system finds its applications in stellar dynamics. In particularly, we are interested in describing the equilibrium state of the center of galaxies with a large number of stars. In this context, we aim to construct mathematical models of matter orbiting black holes by providing stationary solutions to the Einstein-Vlasov system. So in order to motivate the equations, which are seen several times in this workshop, let us think of the galaxy as an isolated system described by a four-dimensional manifold. We assume that there exists a local coordinate system such that x0 is smooth, monotonically increasing function along any causal curve, and its gradient is path-directed and time-like. We denote by v alpha the corresponding four-velocity vector. As for the matter field, the particle ensemble is described by a positive distribution function defined on the tangent bundle of the space-time. We assume that collisions between particles are neglected so that only gravity is taken into account. For physical reasons, we require that all particles move forward in time, and we assume that all particles have the same rest mass m. In this context, we introduce the mass shell defined by the condition that the Lagrangian is of a free falling particle is normalized to minus m squared. The mass shell condition allows to express V0 in terms of V's, which make from gamma m a seven-dimensional subbundle of the phase space. From now on, F will be supported on gamma. Now we define a natural form, volume form on gamma, which is defined by this following definition. So now we introduce the Einstein-Vlasov system. So F has to satisfy the Vlasov equation, which is given by equation 1 in the adapted local coordinates. We coupled it to the Einstein field equations via the definition of the energy momentum tensor given by definition 3. So that 1, 2, and 3 form the so-called massive Einstein-Vlasov system. So in vacuum, the Einstein field equations with the zero cosmological constant reduced to Ricci is equal to 0. A less trivial explicit solution is given by the Schwarzschild, and it describes a non-rotating static, spherically symmetric black hole with mass m. A second non-trivial explicit solution is given by Kerr metric and describes a rotating stationary axis-symmetric black hole with mass m and angular momentum a. So there exists a broad variety of static and spherically symmetric asymptotically flat steady states, as well as static and spherically symmetric solutions with non-vanishing cosmological constant, with the property that the Vlasov field is spatially compactly supported and possesses a finite mass. I apologize in advance because I couldn't mention all the papers related to the construction of steady states because the lack of time. So the most relevant work to our purposes is the one provided by Prof. Gerhard Rhein concerning the construction of static and spherically symmetric solutions with singularity at the center. His approach was based on extension techniques used for the Vlasov-Poisson system. In the context of axis symmetry, up to my knowledge, only two constructions exist in the literature, which were provided by Andreasen, Rhein, and Kunz. The obtained solutions do not contain black holes, and they are close to the Newtonian spherically symmetric steady states. So very recently, Andreasen provided the first construction of spherically symmetric black hole steady states for the massless Einstein-Vlasov system based on arguments from Rhine's results. So now we assume that we are looking for static and spherically symmetric spacetimes. We assume that the distribution function is static and spherically symmetric, so that F is invariant under the complete lift of the space-time Killing vector field. So thanks to the symmetry assumptions, so the quantities, the energy of the particle, the components of the angular momentum are integrals of motion. Also, the rest mass of, or the Hamiltonian of the particle is conserved, and the modulus or the total angular momentum is an integral of motion. So since we are looking for solutions close to Schwarzschild, we fix the background manifold to be the exterior region of a Schwarzschild spacetime of mass m, parameterized by the Schwarzschild coordinates t, r, theta, and phi. We assume that the metric has the following form, the following standard ansatz, where lambda and mu are functions of r only, defined on 2m infinity. We also assume that for now that the distribution function f is a function of E and L. Note that f satisfies the Vlasov equation because the energy and the angular momentum are conserved along the geodesic flow, so that any function of the latter is conserved along the geodesic flow, in particular f. Note also that this ansatz is not the final ansatz for a reason that I will explain in the upcoming slides. So now I state a first version of the main results. So if we fix a positive m, then there exists a one parameter family of smooth, static, spherically symmetric, asymptotically flat spacetimes, and a distribution function f, which is defined on the mass shell, solving the Einstein-Vlasov system given by equations 1, 2, 3, with delta positive, which describe a shell of a Vlasov matter orbiting a Schwarzschild-like black hole of mass m and bifurcates from the Schwarzschild solution. So the bifurcation is defined in the following sense. When delta is 0, f delta identically vanishes and G0 is given by the Schwarzschild of mass m. And when delta is positive, f does not vanish on its support. Most previous works, such as the work of Prof. Gerhard Rein, are based in particular on extension techniques used for the Vlasov-Poisson system. By trapped geodesics, time-like geodesics, or bounded time-like orbits, I mean time-like complete geodesic whose projection in the radial direction lies in the compact region, in some compact region of 2m infinity. Finally, I note that our construction is valid only near Schwarzschild spacetime. Furthermore, our construction includes a more general support for the distribution function. So we will obtain a one parameter family of solutions by perturbing off Schwarzschild spacetime via the implicit function theorem. To this end, we introduce a bifurcation parameter delta, and we adjust the ansatz for f so that the dependence on delta becomes explicit. So when delta is 0, f0 identically vanishes, and when delta is positive, f delta does not vanish. It is a function of the energy and the angular momentum, which is supported on the set of parameters A bound for which trapped geodesics occur. So finally, I precise that this is still not the final ansatz for f for the following reason. So now, due to Schwarzschild symmetries, the geodesic motion forms an integrable Hamiltonian system. Therefore, the study of the geodesic motion is reduced to the motion in the r-VR plane, given by the equation VR squared plus the potential energy defined by this expression is equal to E squared. Note that EL Schwarzschild is cubic in 1 over R. Moreover, it must be less than E squared along any time-like geodesic. So the classification of time-like geodesics is based on the roots of the equation 4. In particular, trapped geodesics occur if the equation 4 has 3 roots, and trapped non-circular orbits occur when these roots are distinct from each other, which is the case we are considering in our work. So based on the possible values for E and L, we obtain the following classification. So we will have circular orbits, trapped orbits, scattered orbits, and plunging orbits. So trapped orbits occur when EL belong to A bound. So now, given E and L in this A bound, the allowed region for a particle, which is the set of points in 2m infinity such that the potential energy is less than E squared, has 2 connected components, 2m R0 and R1 R2. So if we come back to the shape of the potential energy, so we can see that when EL are in A bound, we have 3 roots for the polynomial. EL Schwarzschild of R is equal to minus E squared. And then we have 2 connected components, 2m R0 and R1 R2. So we have two possible cases. So either the geodesic starts from somewhere between R0 and between 2m and R0 and reaches the horizon in a finite proper time, or the geodesic is periodic, so it oscillates between R1 and R2. As a consequence, the radial support of phi has 2 connected components, so plunging orbits and trapped orbits. Since we are interested only in the trapped ones, we adjust the ansatz for the distribution function so that we get rid of the plunging orbits. To this end, we introduce a cutoff function, psi eta, that depends only on the metric component mu, which also appears in the definition of the potential energy associated to a time-like particle moving in a static and spherically symmetric space-time. So the radial support of this cutoff function lays in the region of occurrence of trapped orbits, and it is equal to 1 in this region. So I'm not going to give more details about the shape of key because lack of time. So, but at the end, psi will always be equal to 1 on the set of trapped orbits, so that f is always a function of the integrals of motion. So now f will be the product of psi eta and phi, which depends only on E, L, and delta. So now I will state a detailed version of the previous theorem. So we fix positive m, and we fix O, the exterior region of a Schwarzschild space-time. So now we choose a compact bounded, we choose B bound, a compact set of A bound with the following properties. And now we take phi, which is a C2 function with respect to the 2 variables, and C1 with respect to the bifurcation parameter, with these following properties. Then there exists delta 0 and a 1 parameter family of functions lambda delta, mu delta, which are C2 with the following properties. When lambda 0, when delta is equal to 0, lambda 0, mu 0 is correspond to mu Schwarzschild, lambda Schwarzschild. For all EL in B bound, the equation that the following equation admits 3 distant roots, R0, R1, and R2, which are close to R0 Schwarzschild, R1 Schwarzschild, and R2 Schwarzschild, and which verify this this condition. And the function f delta is the product of a function which depends only on E and L and the psi eta defined above. And if G delta is given by this ansatz, then OG delta F delta is a static and spherically symmetric solution to the Einstein-Vlasov system, describing a matter shell orbiting a Schwarzschild-like black hole in the following sense. So there exists a radii of the matter shell, which satisfy this condition, such that for if R is between 2m R min or R max infinity, then F identically vanishes, and there exists at least an R such that F delta is larger than 0. So the metric G delta is given by the Schwarzschild metric with mass m in the region 2m R min, thanks to the Birkhoff theorem. And then the metric is again given by Schwarzschild metric, but this time with the parameter m delta, which is larger, strictly larger than m in the region R max infinity. So as I mentioned above, the key idea of the construction is the existence and stability of trapped time-like orbits in spacetimes near to Schwarzschild. So in fact, we define the effective potential associated to time-like particle moving in a static and spherically symmetric spacetime by the following expression. Again, the classification of time-like geodesics is based on the roots of equation 5. So we claim that when the potential energy EL and E Schwarzschild are similar, EL has the same number of roots as E Schwarzschild, and they are close to the roots found in the Schwarzschild case. In particular, some trapped geodesics remain trapped after small perturbations. That is, there exists a delta zero uniform in E and L, such that when mu is close to mu Schwarzschild in some C1 norm, the equation 5 admits 3 distant roots, which are close to those of equation 5 with mu is equal to mu Schwarzschild. Moreover, the roots are unique in the region 2m infinity. So the proof is based on a fixed point argument and the compactness of B bound. Again, the compactness of B bound allows us to define R min and R max, the radii of the matter shell. So before we solve the equations, we choose eta uniform again in E and L thanks to the compactness of B bound, which appears in the definition of the cutoff function psi eta, so that the radial support of F lays in the region R min and R max. So now we apply the implicit function theorem to solve the equations. The procedure is standard once we define the solution operator and the functional spaces. So the Einstein-Vlasov system is reduced to the following system of ADs in the region 2m infinity on the metric coefficients lambda and mu only. So here G phi and H phi depend only on mu and the profile phi. So from the first equation, we can express lambda in terms of mu, so that we are left with solving an ODE on mu only in the region 2m infinity. So after integration, we obtain the following representation formula for mu, where rho is a small and R is large, defined by the following conditions. So R must be larger than the max of R2 Schwarzschild EL, and the rho must be less than R0. So that and 2m plus rho must be less than the minimum of R0 Schwarzschild. So in order to solve mu on 2m infinity, so we use the Birkhoff theorem to obtain mu in the region 2m plus rho. In this case, the solution is given by the Schwarzschild metric. Then we apply the implicit function theorem in the region E to solve mu in this region. In this case, mu will be very close to mu Schwarzschild. Finally, we glue again with the Schwarzschild solution to extend the metric to the region R infinity. So the following slides detail the solving part on E, and no new ideas are brought here, so I'm just going to skip them and move to the second part of the talk. So in this part, I will focus on presenting one of the main difficulties that we encounter during the generalization, which is the stability result of trapped geodesics in the Kerr spacetime. So now we assume that we are looking for, we assume that the spacetime is asymptotically flat, stationary, axis symmetric, so that the vector fields T and phi are Killing. We assume that we are looking for a distribution function F, which is stationary and axis symmetric, so that it is invariant under the complete lift of the Killing vector fields. So we have the following quantities: E, the energy measured at infinity, and the LZ and the Z components of the angular momentum, which are conserved, plus the conservation of the Hamiltonian. We fix the background manifold E to be RT. So we will work in the the Weyl coordinates. So the coordinates which are suitable to the axis symmetric case. And we fix the background manifold to be the product of R, 0 to P and B, where B is some conformal manifold to the Euclidean metric. We define the horizon to be the set such that rho is equal to 0 and Z is between minus gamma and gamma. We define the axis of symmetry A to be this set. And now we assume that the metric takes the following ansatz, defined by equation 6. Again, we will assume that the distribution function is a product of a function phi, which depends only on E and LZ, and some cutoff function, which depends on the metric coefficients X, W, and sigma, which is just the determinant of the Lorentzian component of the metric. So now I will state a rough version of the theorem, which is under preparation. So we fix an A which is less than M. Then there exists one parameter family of smooth, stationary, axis symmetric, asymptotically flat spacetimes, and a distribution function F delta, which is defined on the mass shell, which solve the Einstein-Vlasov system given by the equations that I defined above. So such that the solutions describe a shell of Vlasov matter orbiting a Kerr-like black hole of parameters AM and bifurcate from the Kerr solution in the sense that when delta is equal to 0, F0 vanishes, and when delta is positive, then then we have a Vlasov matter. So the matter field of the constructed solutions is compactly supported on the set of trapped future-directed geodesics. Again, the construction is based on the existence and stability of trapped geodesics in stationary and axis symmetric spacetimes, which are close to Kerr. So now I will talk about the main difficulties related to the generalization. So first of all, so the geodesic motion in stationary and axis symmetric spacetimes is not a priori integrable. So there are only three integrals of motion: the conservation of the Hamiltonian, the energy measured at infinity, and the azimuthal angular momentum, which makes the selection of an open set of trapped geodesics harder than the spherically symmetric case. In particular, the construction of A bound in stationary and axis symmetric case is harder than in this case. So key idea is to revisit the time-like geodesics in Kerr and characterize the trapped geodesic motion and future-directed motion based only on E and LZ, despite the integrability of the geodesic motion in Kerr. I note that in Kerr there exists the Carter constant, which is a fourth integral of motion, which separates the R motion from the theta motion. Moreover, one needs to define a two-dimensional potential, and to generalize the notion of turning points. So the turning points, I recall, they are the roots of the equation EL of R is equal to E square, which are no longer points in our case, but curves in the B plane. Another difficulty that arises is that we cannot solve the field equations in just some fixed region of the domain of outer communications, as we have done in the spherically symmetric case. Well, I recall that in the spherically symmetric case, we had to solve the equations only on E, which is which was defined by 2m plus rho, and which was just the bounded region 2m rho and R. In fact, we have even if we have an analogous to the Birkhoff theorem in the axisymmetric case, it cannot be applied here. Indeed, in the black hole literature, the uniqueness of Kerr family conjecture, which is true if the space-time is actually symmetric, cannot be applied in our case. By the way, this conjecture was proven by Carter and Robinson by reducing the Einstein vacuum equations to a harmonic map system with the boundary conditions at infinity, the horizon and the axis of symmetry and their intersection. And they showed that there exists a unique solution defined on the domain of rho and z. So in static spherically symmetric case, we recall that we only solved the problem in a bounded region of the R domain, and we used the Birkhoff theorem in order to extend the solution in the remaining region, that is 2m plus rho and R plus infinity. So unfortunately, the gluing argument cannot be applied in the axis-symmetric case because of the Carter-Robinson theory requires the boundary conditions at infinity. So we cannot just assume that the metric is given by Kerr. We cannot assume that the metric is given by Kerr from the horizon into the inner boundary of the matter shell, and then is given by another Kerr metric from the outer boundary of the matter shell and to infinity. Therefore, we have to solve the system on the whole exterior region with the suitable boundary conditions on the horizon, the axis of symmetry, the infinity, and the intersection between the horizon and the axis of symmetry. This leads to equations with singular coefficients. In this context, I mentioned the work of Schlappentoft, Rothman, and Chodos on the construction of time periodic solutions to the Einstein-Klein-Gordon system, which bifurcate from the Kerr metric. We adapted their strategy concerning the fixed point theorem to the case of the reduced Einstein-Vlasov system. So now I will talk about how can we generalize the stability of trapped geodesic result to the axis symmetric case. So again, we assume that we recall that the energy and the azimuthal angular momentum are integrals of motion. So the geodesic motion is reduced to motion in a four-dimensional submanifold of the phase space. So the geodesic motion is reduced to the study of the equation, the following equation. So now we define the turning points associated to a time-like future-directed geodesic to be the solutions of the equation GK, which is quadratic in E square, equal to 0. So because of the term because of the term 2W over rho square ELZ, the dependence on the dependence of GK on epsilon cannot be separated, as we have done in the Schwarzschild case. In this case, we cannot write the total energy as a sum of kinetic term and a potential term, depending only on the angular momentum. But we are interested only in solutions to the equation GK is equal to 0, so the turning points, because their number determine the nature of orbits. So in spherical symmetry, the intersection of E and the effective potential LZ which depended only on R, gave us an isolated turning points, which allowed us to determine the nature of orbits. In the axisymmetric case, the effective potential, which is defined by this expression, is a two-dimensional, because we do not know a priori whether a fourth constant of motion exists or not. In the case of Kerr, it exists, but in the general case, we don't know, and that's why we used to not use explicitly the Carter constant to separate the motion. So it's like we still assume that Kerr is not integrable. So in the axisymmetric case, so the effective potential depends is two-dimensional. So the intersection of an energy level epsilon and ELZ will lead to a curve in the B plane, as we have as you can see from in this figure. So in this case, we define the zero velocity curve associated to a time-like future-directed geodesic to be the set of points of the turning points. That is the set of points which solve the equation GK, which solve the equation GK is equal to 0, and this equation is equivalent to equation 7, because we assume that our time-like geodesics are future-directed. So again, the trapped geodesics occur when the trapped geodesics occur when the zero velocity curve admits two connected components, so ZK trapped and ZK absorbed. So ZK trapped is diffeomorphic to S1, and ZK absorbed is diffeomorphic to R. So this case occurs when EL are in A bound, and this A bound is the generalization of the A bound that we found in the spherically symmetric case, in the sense that this A bound depends on the parameters A and M of the Kerr metric, such that when A is equal to 0, this AK bound is just the A bound that we found in the Schwarzschild case. So now, given E and LZ in A bound, in this AK bound, two cases are possible. Since the allowed region associated to a time-like future-directed geodesic, which is given by the set of points rho and z, such that ELZ of rho z is less than E squared than E. So this allowed region has two connected components. So the first one, as we see, for example, in this figure, so the first component is the blue region, and the second component is the component that is close to the event horizon. So here, given E and L are in this AK bound, we have two possible cases. So either the geodesic starts somewhere between ZK absorbed and the horizon and reaches the horizon in a finite proper time, or the geodesic is trapped, so it remains inside the bounded region for all times. So now here is the shape of ZVC. So it's just the projection in the R theta plane. So now, in order to generalize the stability result for trapped geodesics, we will have to parameterize the zero velocity curve associated to a trapped geodesic. So we use the Carter constant as a parameter for ZK, and we can state the following result. So if we take a compact set of this AK bound, so we can there exists a finite atlas that that covers the ZK trapped. I mentioned that A are independent. The domain of the charts is independent of E and L thanks to the compactness of B bound, and phi Ka are either functions of rho or functions of Z. So it depends on whether we parameterize our curve. So now we can state the perturbation. So before we state the perturbation results for ZK trapped, we state the definition of what do we mean by perturbation of a closed curve. So we fix delta zero sufficiently small. So Z trapped is H close to ZK trapped, with H is in is sufficiently small in some norm that will be compatible with the norms that we use for the metric in order to solve the reduced Einstein field equations. If there exists an atlas, a finite atlas of ZK trapped, such that phi A are C1 on A, and the phi A are close to phi K. So phi K is the atlas that covers the ZK trapped, and Z trapped is diffeomorphic to S1. So it's just a definition for perturbations of a closed curve. So now, before I state the stability of results of trapped geodesics for curve space-time, again we define the effective potential energy of a particle with momentum L and energy E, which moves in stationary and axisymmetric space-time, to be the following. I recall I mentioned that when in the case of curve, sigma is just rho. So again, the classification of time-like geodesics is based on the roots of the equation 8. So we have EL, so the equation EL is equal to E. So when W, X, and sigma are close to W, K, XK, sigma K for E and LZ in B bound, E, LK, so the potential energy of a time-like future-directed particle moving in stationary and axisymmetric space-time, and the potential energy associated to time-like future-directed particle moving in Kerr are similar. In particular, some trapped geodesics of Kerr remain trapped after small perturbations in the following sense. So there exists a delta zero sufficiently small so that if we take W, X, sigma, which are close to the Kerr components in some C2 or C1 norm that is compatible with the PDE problem, then for all EL in B bound, there exists a unique smooth curve, which is diffeomorphic to S1 in B, which is close to ZK trapped, such that the points of Z perturbated solves the equation EL rho Z is equal to E. So when W, X, sigma are just the quantities for Kerr, so we have the Z perturbated is just the Z curve. And I recall that delta zero is uniform in E and LZ due to the compactness of B bound. So thank you for your attention, and